Hello guys, welcome to my YouTube channel. Today we are going to look into how to run a Rust application which will blink the LEDs on the STM32 board. In the last video, we have seen how to run a Rust application in the STM32 board. So today we are going to improve that code and we are going to use hard bare metal programming and HAL programming to access the LEDs on the STM32 and make them blink, and we'll use some logics so that it will be exciting for us to look on the board while the LEDs are blinking. So let's dive into the video. As in the previous videos, we were using some other template for Rust application, but that template got deprecated, and now we are going with a new template. You can either create your own template, or I'll in the future I will create a new template for you if you want to take it from my template, or you can use a template that has listed here, the app template from Knurling RS. In this template, you will find that they are using a probe RS, DEFMT, and FlipLink embedded projects. And these all three tools are very useful when you are building a Rust program and implementing it in a embedded systems. So I'm using this template. So for that, I need to copy the link of the GitHub, and you need to have cargo in generate to install in your PC. I already have it, but I'm still reinstalling it. It sure took some time. I'm moving into this folder, and I'm in this folder inside Rust CD YouTube, and here I'm going to use cargo generate, and the link we have copied from the GitHub, and we need to give double dash git options, and then our template. Here I'm going to give it as LED blink. In this project, actually, I'm going to use both bare metal programming and HAL programming. So we are entering into CD, and inside I'm going to open this project in cursor, and inside cursor you can see we have the project structure on the left. I'll just briefly explain the project structure. In .cargo we have config.tml. In this we will be having all the configuration that is related to the Rust, and here you can see that there is a runner. This runner is usually the default cargo run script. So when you type in cargo run, then this will be the backend command that will run. And we have the source inside which we have bin. So each inside bin there is a there will be a lot of RS in this template, but if you can also create your own Rust files here, and we can directly build them using probe RS and directly load them into the embedded system. And we have in down we have a target, inside we have debug. So here only we'll be having our targets binary files, and there are a lot other things like test and different RS files that they have given for examples in the template. You can remove all this example Rust files, or you can keep it and work on with your Rust project. Right now I'm not going to remove anything. I'm just going to create a new files here. So inside bin I'm going to create a new file named as LED blink .rs. I'm going to demonstrate first HAL based Rust application, then we're going to move to the bare metal. First, in the HAL based, you can directly ask the ChatGPT to uh, give you the code, and it will give you the code. But still, you have to make sure that all the addresses that it has given is correct. Because when I got the code from the ChatGPT, I got all the code wrongly, and actually it gave the right code as per the logic, but still it has given me the wrong addresses for the LEDs. Because of that, I'm not able to see the LED blink on the STM32. And later I debugged it and I changed the correct addresses. So make sure when you are taking the code from ChatGPT, don't blindly trust the ChatGPT and use as it is. You need to still make some changes in it so that the code will work without any bugs. So I'm going to get the code from my previous project. This is the HAL code. So HAL is nothing but hardware abstraction layer. So when you're using with the HAL project, then you don't have to worry about the addresses and peripherals that they are using. You can simply take the function calls and use them as it is. So HAL will create a layer on top of the peripherals and every addresses, and you can usually interact with the board. But if you want to still go deep into the address and memory segmentation and if you want to explore the board properly, then it is better to always use bare metal. And in the bare metal you can access every address, every peripheral and everything with the code. But whereas with the hardware abstraction layer, you can't. You can only use the projects, but you can use both hardware abstraction and bare metal simultaneously. So in this code, you can see that we are using no STD, no main, cortex inventory, and we are using STM32F407 HAL. This is the package that I got it from the cargo, and this will be available in the open source. So you directly call it and use it. And we have DEFMTRS, which is a global logger. This will log all the data and errors. And we have panic probe. This is for panic handlers. We have the main function here, and I'm calling this pack peripherals take unwrap will actually call all the peripherals that are present in the hardware abstraction, that is STM32. And the STM32 will be having those peripherals, and it will come into the variable DP. So in the DP you can if you want to access RCC, which is a clock, to enable that you need to give RCC, and in the RCC constraint you can access the RCC, and we can access the GPIO D segment from the GPIO D split. So everything will be present inside DP. So you need to know what functions you need to use. If you are not sure about the functions and everything, you can simply go to the ChatGPT and get the details of it. And even though you're using ChatGPT, please make sure that you are aware of the changes that you're doing on the code. So I'm creating a green LED, and the into push pull output will configure the output of the PD12, that is LED pin. So PD12 is LED pin and PD13 is LED pin 14, 15. So each pin is configured for a single LED on the board. For that, if you want to know why these are there, you need to have the reference manuals available for it. So in the reference manuals will be, so this is a reference manual. Uh, you need to know how to read these reference manuals and search for the memory segments and peripherals addresses. So here you can see that there is a RCC AHD1. So in the reference manual, you will be having this kind of details. Here we have AHB1 as a bus, and in this we have RCC. RCC is the clock register. To enable clock and everything, you have to use RCC. So that's why we use that RCC. And we have different GPIO segments. So we are the LEDs are configured on GPIO D. So I'm using GPIO D in the code. You can see that, yeah. So I'm using GPIO-D, and I'm taking that into the GPIO-D variable. So, and from GPIO-D we can access the LEDs different by using GPIO-D PD12 into push pull output. And initially I'm setting all the LEDs to low. That will it will be 0. I'm using a variable so that I'm looping on the LEDs for every 8 milliseconds. So inside the loop, I'm setting everything to low, and after that, I'm using a switch condition, that is match in the rust, and for every current LED value, I'm incrementing the current LED value at the bottom, and using the remainder function, that is percentage of 4, so that it will always give the remainder of 4, so that we will be having 0, 1, 2, 3, and not above 4. So every time the loop runs, it will take one LED and toggle it, and we'll be printing the log onto the console by using defmt. So this is a logger, so I'm using that logger, and inside that we have println functions, and at the bottom we have panic function. And now I'm going to connect the board to the PC, and I'm going to run this build this code and run it on the board. To run this code, actually you need to first set up few things. So here we have $chip. So we need to remove this and use our board name to get the list of all board names that are supporting in the probe RS. Actually probe RS is a debugging and building tool that will connect you directly to the board. Previously we used to use OCD, GDB and everything working simultaneously to connect. But if you use probe RS, you can directly connect with the board without having any hassle. In the template itself, you have uh, a command called probe-rs chip list. You will find all the chipsets that the probe-rs is supporting right now. If you are not having any chip, if you are using a chip that isn't supported in the probe-rs, you can go with the default GDB and OCD commands and do the hard part of debugging and building the code. And right now I'm using a STM32, so I need to find the STM32. I'll find it. Grep trim F4. So we have all this F407. We need to find F407 here. So there are 5 types, I guess 5 types of F407, and I'm going to use the last one here is STM32 F407 Z, and I'm going to paste it here. And you need to save the toml file, and also make sure your target is set properly. In the STM32 you will be having M4 chip, so you need to enable this target, and you can also find some aliases for running the commands. So you can use the command cargo run --bin and the name of the rs file that we have used, LED blink underscore HAL. No need to give .rs. As you can see, it is building. Yeah, sorry, we didn't add the STM32 HAL package into the packages that is required. So usually in the cargo.toml, you will be having all the packages list. So to add into that, you need to add it via command, or you can directly go and type in the package name. So I'm adding it from the command line. So it is adding, and we can run the blink HAL. There is a issue. We need to figure out what's the issue. The error was because we didn't add the features inside the STM32 HAL package. So for that, we need to add the features like STM32F407 in the features of STM32F4 HAL. I need to save this cargo.toml, and after that we can build the cargo using the cargo RB cargo run. This error is caused because we are not using a memory.ax file. Actually, we need to create memory.x. Usually for a lot of HAL packages, we will be getting a memory.x. But for the STM32F4, we don't have any .x files. So we need to create one by using new file, and here we are going to use memory.x. You have to get the data for the memory. you can either use the previous memory segmentation that we are used in the previous video, or you can get the data from any website, or you can use the reference manual to get the data and the addresses of the RAM and ROM. Right now I'm copying the memory segmentation from the previous video. Now every issue is resolved. Now we can build the code. So as you can see, the code has been built and it is being run on the STM32 board. And I'm able to see that the LEDs are blinking in a circular motion from green, red, orange and blue. Sorry, green, orange, red and blue. And it is running in a loop. So until we stop it, it is going to run. So this is how you are going to run a LED blinking code on the STM32 board. And after this, I'm going to run the same code using the bare metal code. And in that bare metal code, I'm going to use all the LEDs addresses, and I'm going to toggle the LEDs using the same logic as we did in the HAL. Now we are jumping into bare metal code. For this, I'm going to create a new file inside the bin. This will be LED click covers. So for this also, I took the code from the ChatGPT and I'm going to paste it directly here. Actually, there were a lot of problems when I got the code from the ChatGPT, but still I debugged it and I changed the code as per my requirements, and I'm using this here. So this is the code for the, so in the bare metal programming that we are using, importing DEFMT for logging, and panic probe as that is required for the panic handling, and STM32 HAL. This STM32 HAL will uh, import the interpreters that are linked to the crate, and we are getting the address of RCC from the AHB1 bus, that is 400233830. I got this address from the reference manual. You can search in Google for the reference manual with the chipset that you are using. For my example, I'll be using STM32, so I'll search in Google with STM32 reference manual, and you will find the reference manual in the official website of the STM32. And after getting that reference, you need to search for the RCC address, and after that you can take the address of the GPIO demodder, that will be 40020C00, and the GPIO ODR, this will be the output data register, and the address will be 40020C14. Why this ODR? This address is related to the LED, and from this address only we are going to toggle the LEDs. So in the main function, I'm going to enable the RCC, which will be the clock address for the GPIOD. So for the GPIOD, we need to set the third bit. So for that, I'm using the write volatile function, and I'm shifting the 1 to the third position, and then writing it in with the and I'm doing OR operation in between with the AHB1 NR, and I'm writing it into the RCC address, by which by using this operation we will be able to set the third bit of the RCC address. And we are using, and I'm reading the GPIO ODR address, and I'm taking it into a mutable variable, and we need to make sure that you're using a mutable variable, or else you can't change the address and toggle the LED. And there is a modder which will set the in and out input. It will set the input and output of the LED blinking. So in the modder address, we need to set the LEDs at the as outputs. So by setting the bits of the modder at 24 and 25, we will be enabling the output of the green LED. And likewise for orange LED, it will be 26 and 27. and for red LED it will be 28 and 29, and for blue LED it will be 30 and 31. As you can see, there is a pattern here for every pin of LED, which will be 12, 12th, uh, the 12th pin of GPIO D is the green LED. So the twice the number, the multiple of 12, that is 24. 12 into 24 will be the bits that will enable the green LED. And likewise for orange LED, it will be 13 into 2, that will be 26 pin. And likewise for LED, 14 into 2, the 28th pin. And for blue LED, 15 into 2, 30 pin. So we have to enable the all the pins for the as output, and then only we can able to see the LEDs blinking. And after that, I'm using a current LED variable, which is a mutable variable, and I'm writing a loop function inside this. And here we are turning off all the LEDs by writing 0 into the pointer ODR, GPIO ODR pointer. And in the switch statement, we are toggling the pointer using OR function, and we are setting each pin like 12, 13, 14 and 15 for every LED, for each LED. So for green LED it will be 12, and for orange it will be 13, and for red it will be 14, and for blue it will be 15. So for each loop iteration, it will blink the particular LED based on the number of shift of 1 and OR operation of the GPIO ODR. And we are adding a 8 milliseconds delay, and the same on the same condition that we use in the HAL. So this is how you're going to code in the Rust using HAL and bare metal programming. Let me know down in the comments that what type of programming you would recommend me to use in the future. In the future, I'm going to use mostly HAL based and sometimes bare metal code, but it will be mostly the combination of both. And please let me know down in the comments what your preference is. And also I'll be posting this in the Git so that you can clone it, play with it around. You can change the logic of the LEDs blinking. You can change how the LEDs toggling can happen. Play around with it and you can learn more about it. Thank you. And don't forget to like, share and subscribe.